Hi, welcome back. This is Professor Ridge, and today's lesson is on section 2.3, the composition of functions. The composite function f composed with g is or you can say the composition of f and g is defined as, okay, again I read this as f composed with g of x equals f of g of x. And so that's the composition of functions. So this is basically the definition of composition. Memorize that. And just note, x has to be in the domain of g, and then g of x has to be in the domain of f. Okay, let's look at some examples. So if I define f of x to be 3x plus 2, and g of x equals x squared minus 1, find the following. So f composed with g. Now we can do it with a single x coordinate, say like 2. And so by definition from above, we're going to write f of g of 2. And the way to think of it is, you're going to plug 2 into g, so you got to do that first. So g is defined to be x squared minus 1. And notice how I left that blank there, because we're going to do g of 2, so it's going to be 2 squared minus 1. So we have 2 squared minus 1 is equal to 4 minus 1, which is equal to 3. And now you're going to plug 3 into the f function. Well, the f function is 3 times x plus 2, and we're plugging in 3 for the x. So 3 times 3 is 9, plus 2 is 11. So f composed with g of 2 is equal to 11. Let's try another one. How about f composed with g of 4? So again, we're going to do definition f of g of 4. And then we're going to plug the 4 into the g function. G function is x squared minus 1. So I plug in a 4 for the x. And I get 16 minus 1 is 15. Now we're going to plug the 15 into the x. So 3x plus 2. Plug in the 15 in. So that gets me 45 plus 2 is 47. So f composed of g of 4 is 47. Now, what happens if we switch the order, if we do g composed with f of 4? Well, by definition, we're going to go g of f of 4. Plug the 4 into the f function first, and the f function is 3x plus 2. Plug the 4 in. So now we're going to get 3 times 4 is 12, plus 2 is 14. Now we're going to plug the 14 into the g function, which is x squared minus 1. Plug the 14 in for x. So that is 196 minus 1, which is 195. And notice you get a different answer than we did in, f composed with g of 4 was 47, while g composed with f of 4 is 195. So in general, you can't switch the order and get the same result. In special cases it will, but in general you can't switch the order. So again, we can do f composed with g now of just a letter, just the actual x. So it'll be f of g of x. So that'll be f of g of x was given to us to be x squared minus 1. And now f is 3 times x plus 2, but now we're not doing f of x, we're doing f of x squared minus 1. So we plug in the x squared minus 1 where the x was, and use some algebra to simplify this. So distribute the 3, and then add the 2. So we get 3x squared minus 1. So that's f composed with g of x. Let's look at another example. Find f composed with g of x and state the domain of f composed with g given f of x is 4 over the quantity 1 minus 5x and g of x is 1 over x. Okay, so A and B is the domain. So for A, f composed with g of x, again we're going to apply the definition. That's f of g of x. G of x is 1 over x. And then we're going to put 1 over x in for f. So f is 4 over 1 minus 5x, but we're going to put 1 over x in there. So we have this complex fraction, and we need to do a little algebra to simplify that. So if you recall, you're going to multiply everything by well, first let me distribute it. Not distribute it, but just multiply it out. So it's 5 over x. So to simplify this, I can multiply everything by x over x. So that's going to get me 4x over x minus 5. Okay, so f composed with g of x is equal to 4x over x minus 5. So that's part A. And part B is what's the domain? Well, the domain of f is whatever makes the denominator equal to 0, you got to exclude it. So we're going to say, all right, 1 minus 5x cannot equal 0. Oh, I'm sorry. We don't need domain f. We got to start with the inside. The domain of g is what makes x not equal to 0. So remember, when we're doing f composed with g of x, we're starting on the inside, so we got to look at the domain of g of x first, and then so we got to note that g of x, the domain of g is x cannot equal 0, so we got to consider that. And then when we do f of g of x, we look at that final outcome, which is 4x over x minus 5, and we note that, well, x minus 5 cannot equal 0 also. So x cannot equal 5. So you got to consider the final result, and you got to consider the inside function, what's not allowed. So for g, if x was 0, I can't even begin the process. And also in the final result, f of g of x, x cannot be 5 either. Okay, so we got to throw out both of those things. So you got to consider the inside function. So g of x is, remember, 1 over x. So x cannot equal 0, because if you have a fraction, the denominator is not allowed to be 0. And then in the final result, the denominator is x minus 5, so that can't equal 0. So you got to throw out 5 also. So our domain of f composed with g is equal to, we do interval notation, negative infinity to 0, 0 to 5, so we're throwing out 0. We're throwing out 5, that's why we have parentheses, and then 5 to infinity. So basically it's everything but 0 and 5. Okay? Alright, let's look at decomposing a function as a composition. So let's look at this example. If h of x is 3x plus 2 quantity squared, find f of x and g of x such that h of x is f composed with g of x. So basically the way I think of this is, f composed with g of x by definition is f of g of x. So we have this inside function and then the outside function. So g of x is what the thing that we're going to do first. So you can think of it as like order operations. If I gave you, so we have our function 3x plus 2 squared, and if I asked you to tell me if I picked the number for x, say 5, by order operations, what steps would you do to get me a number for this? So if x was 5, so say 5, what are you going to do first when you plug it in to the expression to simplify it? Well, you're going to multiply it by 3, then you're going to add 2, and then you're going to square it. So that's the order operations. So what we need to do is basically we're going to split this up into two separate functions and just mark a line somewhere. And the most natural place would be, if you think of the big grouping, the parentheses, that's a good place to split it. But I could split it after the multiplying 3. So basically this I'm going to make g, and then the squaring I'm going to make f. So g of x is going to be the inside of the parentheses, the 3x plus 2, and the f is going to be the squaring. So we reset it back to x, so it's x squared. So now let's do a check just to see if we did that right. So let's see if we had that. F composed with g of x, the f of g of x. Then you'll see that g of x is the 3x plus 2. And then we're going to plug, then f of x is x squared, so we're going to take the parentheses, plug in the 3x plus 2, and square it. And we get the function h of x that we're going for. So that checks out. So our answer is g of x is 3x plus 2, and f of x is x squared. So note, I could have also done it this way. I could have split it after the 3. So if I did the multiply by 3, add 2, and then square it, see there's 3 steps. So if I want to split it into 2 functions, I could split it there. And this would be my g, and then this would be my f. So g of x would be, we're going to multiply x by 3, so that's 3x. And f of x could be, you're going to, okay, so you reset it to x. So we're going to take x, add 2 to it, and then square that quantity. And if we check it, f of g of x would be equal to 3x, and then f is the x plus 2, so I'm going to leave parenthesis there. Take the x out, put in 3x. So you get the 3x plus 2 squared. Checks out to h of x. Okay? So either answer would have been acceptable, so you can get different answers. Okay? So just kind of think of it that way, you know, think of it as OR operations and just split it into two separate functions, and there you go. So that's decomposing a function as a composition. Alright, let's look at one more example of that. I noticed this one. The technique that I showed you above may not work too well for this one. I mean, it could, but the thing that I would notice is both the top and the bottom of this rational function has an x cubed. So if you let g of x be that x cubed, and see that this is going to work because both the top and bottom have the x cubed, I can let that be my g of x, and then my f of x is going to be okay. So now wherever you see the x cubed, reset that as x. So that's going to be x minus 1 over x plus 1. And if you want to check it, f composed with g of x is f of x cubed. And then remember, f of x is x minus 1 over x plus 1, and we're going to plug in an x cubed. And we get h of x, which is what we were going for. So that checks out. Alright, so sometimes you got to get a little creative, and you know, if I notice the top and bottom has the same x term, I might do that. That doesn't always work, but you just have to get creative and try some things. But generally, if you do like the technique above, you know, think of order operations, that generally works. Okay, so that completes the lesson for 2.3. Go to MyMathLab and complete your exercises there, and I'll see you next time.